Hello everyone, my name is Harini and this project was completed with my partner Echo. In this presentation we'll be speaking about our product, HeliSpin. With a growing concerns towards depleting fossil fuels, greater than 22% of the generation of electricity is revolutionized through green energy movement according to Aerodynamic. Wind energy, being one of the most abundant forms of renewable energy, currently performs with lower efficiency and produces adverse impacts on our environment. The traditional wind turbines are made from carbon fiber reinforced plastics, which are difficult to recycle, and its massive scale structures hinders its ability to collect energy in the fluctuating wind profiles. Furthermore, its implementation in rural areas limits its applications in agriculture, and its massive size harms wildlife populations. HeliSpin is a compatible, innovative, and eco-friendly wind turbine solution that can be operated in urban regions where copious amounts of kinetic energy is observed from the movement of vehicles. The prototype's mechanism is actually inspired by the autorotative traits of helicopter seat as represented in this image. According to nonlinearity, the streamlined patterns are the key to increasing the lift force and decreasing the friction along the angle of attack as represented here. Therefore, the helicopter seat was considered as an airfoil in the situation where these forces were calculated in their cross-sectional views. From our research, we initially predicted that if the lift force is greater, along with slight loss of thermal energy under laminar fluid flow conditions or stable fluid flow conditions, then the power efficiency of the nature-inspired model will be boosted compared to the traditional blades in greater frequency of rotations. In other words, the aim of this experiment was to connect the aerodynamic performance with power efficiency through calculating the frequency of spins under multiple blade quantities. For the first portion of the study, computational fluid dynamics was utilized to comprehend the influence of fluid forces in the aerodynamic performance of the blades under laminar 5 meter per second and turbulent 50 meter per second conditions. One of the challenges that we encountered when completing the CAD modeling was that the model wasn't traced as accurate as the complex patterns of the helicopter seat. Therefore, only the highlight features such as the tubercles and the pod were modeled in rough layers for the CFD simulation and physical testings as represented in this image. The next step was simulation. OpenFOAM uses the finite volume method to calculate the parameters with mass, momentum, and energy preserved in each cell of the mesh. The Navier-Stokes equations are the partial differential equations that will be discretized to compute the solutions. The conservation of mass represents the rate of change of mass is equal to the total inflow of the mass in the control volume of one single cell. The same phenomena is applied to momentum as well as energy, wherein other forces like pressure, viscous force, and body forces are taken into consideration.
The physical testing involves designing a wind turbine with blades, embedded helicopter seat patterns, and proving that its aerodynamics would lead to a better power efficiency. This was split into 6 steps. Initially, we did CAD modeling to show the major mechanical aspects. The blade profile with a diameter of 10.9 cm were traced by 3D printing pen in different layers using eco-friendly PLA filament to maximally simulate helicopter seats. The power meter was used to track the voltage and current. When connecting the circuit, a diode was used to cut off the power supply of DC motor. Finally, the turbine blades testing was driven by the mechanicisms of vehicles on the street, where the mechanical energy converted to electrical energy.
For the first portion of the study with computational fluid dynamics, the drag coefficients and lift coefficients were calculated in plus x and minus y directions in the cross sections of the airfoil. According to the graph represented here, the bending points follow a similar trend, showing that the statistics from the simulation remains predictable. For the laminar flow, the drag coefficients are decreasing over a low force acting on plus x horizontal direction. For the pod-contained model, the drag reduction is less significant than the non-pattern model because these patterns exhibit skin friction drag. According to Bernoulli's equations, slow-moving upstream velocity will result in greater pressure for the streamlined model. There is a greater loss of energy in the laminar model compared to the non-pattern model. The thickness of the pod exhibits friction, and this contributes to lower lift coefficients. On the other hand, HeliSpin turbine blades have the best performance in turbulent conditions. Due to the greater amount of eddies created in the non-pattern simulation, there was a greater amount of friction produced in the edges of the model or the airfoil. The pod-contained model was effective at overcoming these turbulent wakes under fast-moving fluid conditions, and this resulted in lower pressure and less dissipation of energy. Therefore, the bending point is slightly pointing upwards on both of the graphs, stating that there is a greater lift coefficient that increases the acceleration of the wind turbine.
Further physical testing results. The physical testing data was collected with the aid of the power meter under 15 meters per second constant wind speed. Our tested variables include blade quantities that will influence the power coefficients and rotational speeds. The power coefficient was then calculated with controlled wind power, which is 18.68 watts. According to the results on the Part B graphs, all the power coefficients were less than 59.3% efficiency from base limit. Two-blade pattern had the greatest rotational speed but lower power coefficients, and the three-blade turbine works the best because it has the moderate rotational speed and the greatest power coefficient. In conclusion, our hypothesis was partially supported by the experiment since the helicopter seat's blade performed more efficiently in turbulent conditions. The two-blade and four-blade pattern failed to satisfy the power efficiency conditions because the two-blade turbine has the greatest rotational speed that will result in dissipation of energy from drag forces. And the four-blade pattern adds a greater weight to the turbine, showing that there will be an increase in force acting in y direction and decrease in lift coefficients. Three-blade pattern has moderate rotational speed that exhibits less drag and greater lift coefficient.